Okay, let's start everything here. I will start recording now. Okay. Good morning, everybody. Welcome again for the last talk of this year before holidays. And today we will have the talk by Dr. Laura Wolz, and she will talk about cold gas constraints via H1 intensity mapping in the SKA era. So thank you very much, Laura, for this talk. And John Alberdi, our director of IAA, will make the formal introduction. And John, please.
Okay, thanks a lot, René. And thanks a lot, Laura. Welcome to our Severo Ochoa IAA weblog. Dr. Laura Wolz is a Presidential Fellow at the Jodrell Bank Centre for Astrophysics at the University of Manchester since the year 2019. In 2021, she was awarded the UK Research and Innovation Future Leaders Fellowship to support her research in mapping the cosmic web with neutral hydrogen during the era of the Square Kilometre Array. She's working in the field of cosmology since her physics undergraduate in Munich, Germany. She completed her PhD at the University College London and joined the University of Melbourne as a postdoc fellow, followed by a fellowship through the Discovery Early Career Research Award from the Australian Research Council. Laura specializes in cosmology with radio surveys, particularly the mapping of the large-scale structure of the cosmic web, via the radio emission from cold gas in and around galaxies. Laura is deeply involved in the planning and preparing of cosmology surveys with the upcoming Square Kilometre Array Observatory and its pathfinders, having co-chaired the Cosmology Science Working Group for 4 years. And she is currently co-leading the H1 Intensity Mapping Focus Group within it. She's dedicated to creating a diverse and welcoming environment in astrophysics and academia in general. Today, she will talk about cold gas constraints via H1 intensity mapping in the SKA area. Laura, the floor is yours, and thanks for accepting our invitation. Welcome.
Thank you very much. Thank you for that introduction. All right. It's a pleasure to talk to you today, and thanks for joining, especially for the last colloquium of the year, or semester, whatever it is. Let's jump straight into it. Let me give you an outline of the talk. So first, I'm going to introduce H1 intensity mapping, what the technique is, what we are trying to do, and the sort of surveys and instruments we use to do that. You can already guess we want to use the SKA Observatory for H1 intensity mapping. So I'll talk a little bit more about the SKA and also showcase one of our recent projects within the working groups. And then very excitingly, I'm actually going to spend most of the time showing you the latest data. And that will be for single dish intensity mapping from the Green Bank telescope and MeerKAT, and then interferometric intensity mapping. It will also be some MeerKAT data at the very end. All right, so H1 intensity mapping. It is a relatively new probe in order to observe the large scale structure, so that we can infer the underlying cosmology from it. So in this upper left map, you can see a simulation, the Millennium simulation, in the gray shades, the underlying dark matter structure. And then in these blue stars, you can see how some, and these are very star-forming blue galaxies, trace the underlying dark matter. And so this is one way that conventionally we observe the galaxies and then we infer cosmology from it. But now I want to talk to you about how we can do it not by using the starlight from the galaxies, but by using the emission from the cold hydrogen gas. So cold hydrogen gas has an emission line at 21 centimeter, which is called by the spin flip of the electron in the shell. And when the spin flips from aligned to anti-aligned, it emits this 21 centimeter emission. So in H1 intensity mapping, we use this emission from basically all the cold gas that there is to observe it with a radio telescope. So we do a continuous mapping without identifying any objects, and we really integrate over all the H1 emission that's coming. And so it's a bit like a CMB observation. We are probably a bit more used to seeing these CMB maps. And you can see in the lower map, just again, a simulated example, how then this would look like. Now, the beauty of using this redshifted line emission is that we get very high redshift resolution, because basically every frequency channel of our telescope will give you a different redshift. And another advantage of this method is that we can do it for a really wide range of redshifts continuously if you have the telescope to do so, and really observe very, very large volumes, ideally the whole universe if we can. Now I've got a little bit of a movie, which again just shows you graphically how intensity mapping works. So you saw this cartoon of the large scale structure with all these galaxies within it. And then you basically have in the galaxies the cold gas, which emits the radio emission, and then it travels towards us. And we can then observe it with a radio telescope. And now in this little movie, you will see here the Parkes telescope, which is I think 64 meter-ish in Australia. And you can use that to do these intensity mapping observations. And you can see here again how basically every different redshifted line goes into a different frequency channel. So you end up with having these really fine resolution in redshift direction or frequency direction, but we have quite poor spatial resolution on the mapped space, as you can see on those maps here. Okay, so then what we do with these maps usually is that we look at their power spectrum, which is the Fourier transform of a 2-point correlation function. So we're looking at overdensities as a function of inverse scale. And so you can see here, just again, a quite schematic view of a power spectrum where you have the blue line, the Planck fiducial model. And then if I play around with the underlying cosmology, for example, increase dark matter density in the green dashed lines, or add some evolving dark energy parameter in it in the dotted line, the overall shape and a bit of also the amplitude will change of this power spectrum. And this is then how we test for different cosmology when we have observed these H1 intensity maps. Now, it being H1 intensity maps, so it measures the brightness of H1, which again just goes down to how much H1 mass is there in galaxies around it. Also goes into the amplitude of this power spectrum, because we're not just looking at like in galaxy service at dots of galaxies and counting them. We're actually having an amplitude of the temperature. So you can see here that we are measuring in terms of Kelvin a temperature. So if we have more or less H1 overall in the universe, the cosmic H1 density, omega H1, the amplitude will also go up or down. Now we can also use the features of the power spectrum, which is somewhat easier than trying to do an overall shape, sort of constrain the overall shape. And so examples of that would be, you could on the very large scales use redshift space distortions, or the larger scales are also very sensitive to non-Gaussianity and modified gravity parameters from the early universe. We can test the matter radiation equality, or we can measure the baryon acoustic oscillations, which are here these wiggles in this power spectrum, which is very much the sort of standard approach if we want to measure the acceleration of the universe, the dark energy parameters that we try to test for the baryon acoustic oscillation, which is much more robust than trying to fit the overall power spectrum. And then on the smaller scales, we can also look for more like non-linear effects of environments or galaxy information. But now again, because we are using H1 as an observable, there will be other factors that go into the shape of the power spectrum, which don't come from the underlying cosmology, but from the H1. So I've already mentioned the cosmic H1 density, omega H1, which is directly proportional to the temperature of the maps, which will go into the power spectrum. So that's the overall amplitude. Then there's also an H1 bias, which you can see here on the left, an example from a simulation. So you can see that for redshift 0, we expect it to be really quite scale dependent, especially on the smaller scales. So we need to take that into account, but also we want to constrain it because we can learn something about how H1 is distributed with relation to dark matter. And then there's also a third sort of observable, which is the H1 shot noise. So from galaxy surveys, you might be familiar with shot noise. This comes from the fact that you have a finite amount of galaxies in your survey. So you will hit a noise plateau like this here, which is just the inverse of your number density. Now for H1 intensity mapping, because again, we are not just counting galaxies, but we have different temperatures. So not all galaxies will emit the same amount of H1 radiation out because they have different masses. And that is slightly more complicated. And it's actually really interesting to measure that shot noise because it can tell us about how H1 is distributed in the galaxies. So your power spectrum would look like something like this in a very simplified form. So you have the temperature, the omega H1 that goes into the bias, which can be scale dependent. Then here is all your cosmology, and then you also have the shot noise factor, which is again very interesting in the perspective of the cold gas. So now, how do we observe H1 intensity mapping? We use radio telescopes. So the redshift of 21 centimeter emission means that we observe usually in the L band it starts. So we start with frequency smaller than 1.42 megahertz and can basically go down as far as we can to go to higher and higher redshifts. And we can do different types of observations depending on the instrument we have. We use a big single dish like you've seen with the Parkes telescope or here the Green Bank telescope, or we can use an interferometer. And here I show you an example of the MeerKAT array. Now the instrumental setup will have a quite big influence on what you're actually going to measure in your power spectrum space. Because if you use a single dish, you will have a very poor spatial resolution of, we're literally talking about a degree resolution or a half a degree resolution on the sky. So you won't be able to see any of these small scale information on the power spectrum. So you're only able to constrain this part of the power spectrum and all the information that is in there. However, if you use an interferometric setup like a dish array, you can then only see what's within that beam, so you're not sensitive to the large scale information. So the one thing which is sometimes a bit tricky is that also the BAO can, especially for the SKA, sits a little bit in the middle here. So depending on the redshift we're looking at, we need to see which data we can actually use to measure the BAO scale. Right, so ongoing experiments, just very quickly, ongoing or that have taken data. The Green Bank telescope was in the US, was pioneering with intensity mapping observations. Then the next one to detect it in cross-correlation was the Parkes telescope in Australia. And now ongoing experiments are at CHIME. They actually had a publication out just a couple of months ago, but I'm not going to talk about this here. And MeerKAT, but also the Australian Pathfinder ASCAP could be used to do observations like that. And now you see that MeerKAT and ASCAP are in a sort of like shaded yellow-red regime. And that is because if you have a dish array, you can actually use it as a single dish, like just a bunch of single dishes, or you can use it as an interferometer. So you can actually measure the whole power spectrum with two different types of experiments with the same instrument. And I'm going to show you loads of that later in the talk. Okay, so that's just a very quick summary. So we're all on the same page about what H1 intensity mapping is and what I want to talk to you about. So we want to test the large scale structure, and the dark matter distribution can tell us loads about the cosmology, the early universe, dark energy, and so on. But because we are tracing it with the H1 gas, we also have loads of information about the hydrogen gas in it and how it traces the dark matter, but also how it evolves with time. And then we can observe this with the telescopes, and depending on the instrumental setup we use, that telescopes, we will be sensitive to different parts of the power spectrum, and that also means there's different things we can test with the data. Now, challenges. We get them right out of the way. Obviously, if it was so easy, you might have seen much more data and constraints about it already on it. But it's very challenging. You need a very good radio telescope in order to do these observations, because the H1 emission is intrinsically very weak, and it can be weaker than just the receiver noise of your telescope, or of the same order of magnitude. So even that, and then receiver noise can also have like a 1/f, like a frequency dependence in it, and all of these things. So even that can be a bit challenging, and you have to know what you're doing with your instrument in order to distinguish those. Because we're doing a continuous sort of scanning of the sky, there's loads of other instrumental errors which become really dominant in it. You need to know your calibration. You need to know the stability of your calibration. You need to know the beam of your instrument really well, particularly if there are side lobes present. Pointing errors could be a problem, and we do know that polarization leakage is also a problem in the maps. A way around that is, again, you want to simulate your instrument's response really well and test your method on both simulations and data and compare. And that's a lot of ongoing work at the moment in order to prepare for more data. And now I think the two biggest challenges that we are facing now is basically contaminations. One is human-made contamination, which is RFI, radio frequency interference. It can be time dependent, it can be direction dependent, and it's frequency dependent. And you don't really know where it's coming from and what is causing it always. We know that satellites are a problem. Obviously, radio communications can be a problem. Even your own instrument can leak RFI from like cables in there, or like a neighboring instrument. So RFI is a really difficult one, as it at the moment means we have to throw quite a lot of the data away because it's just too contaminated. And then the biggest challenge is that we are actually sitting also in a lot of foreground, like now we're talking astrophysics. So our own Milky Way produces radiation at the same frequencies, which is mostly synchrotron, but also some free emission. But then also we have a lot of just radio galaxies, again with synchrotron emission and so on, that we need to remove. And these foregrounds are really orders of magnitudes higher than the actual signal. So you need to test and know what you're doing really, really well in order to remove foregrounds. And there's probably quite a lot of sort of recent papers here to add to my list as well. This is, I think, quite incomplete now, which is fantastic because it means more and more people are working it and facing these challenges. Okay, so talking a little bit about the SKA. So you probably all know the SKA, just a very quick, here we have lucky to have the SKA headquarters here at Georgia Bank. So you can see here the Lovell telescope above the SKA headquarters. And then at the moment, there are 8 member countries who have officially ratified this intergovernmental organization, the SKA, which are obviously the host countries for the telescopes, but also others. And then there's a lot of prospective members talking with the SKA and hopefully joining sometime soon. So it's a very global experiment. And as a global experiment, it also has 2 instruments and 2 continents. We have the SKA mid array, which is this dish array, where you have dishes of 30.5 meters, and some are 15 meters. It's a mix of both of these, so relatively small comparatively to other dishes. And you're going to have about 200 at the end, and that's going to be based in South Africa. And the frequency range you can see here starts with 350 megahertz, which would be for H1 intensity mapping about a redshift 3, I think. Yes. And then there's also the second array, which is the SK low array, which is going to be these stations of antennas. They're dubbed, I think, the Christmas trees, these little antennas, because they look like little Christmas trees. So you have about 256 of these antennas per station, and then again more than 500 stations in the Australian desert, and they are the low frequency. So the main science there is detecting the apocryphalization, but we can also do actually H1 intensity mapping for some of that frequency range. Now, in sort of recent years, we have worked on putting our sort of cosmology case for the SKA together, and we had a red book. So if anyone is interested in that, that's a really good start. It's obviously it's a big paper. We called it a red book, so it's more that, but it has loads of chapters and they're quite independent. So if one wanted to know about something specific about the SKA in terms of cosmology, that's a really, I think, a good way to start. Reading some parts of it or looking up some of the predictions that we have made there. And so basically our cosmology science goals are quite generally, I think, what a lot of cosmology surveys, also in the optical, want to do. We want to test dark energy, modified gravity, non-Gaussianity, and dark matter. Now, obviously, being a radio experiment, we also want to test the H1 evolution for redshift 0 to 6 and the cosmological principle as well with the radio observations. And then we have these proposed surveys. So this is just what we based our red book on. It's not what's necessarily going to happen, but obviously we're hoping that's going to happen, which are 3 surveys. And for H1 intensity mapping, these 2 are the relevant ones, which is a wide survey of 20,000 square degrees with the SKA mid, so that's a dish telescope. For redshift 0.35 to 3, and then we want to use the low part, so the stations in Australia to do the high redshift part. And then these are some of the cosmology things we can do, because I'm going to talk much more about just H1 for the rest of the talk. So I just want to point them out. There's lots of cosmology you can do with H1 intensity mapping. And these are predictions for how well we can constrain the power spectrum with mid telescope, and for high redshift with a low part of the SKA. We can constrain dark energy, parameters of state, as you can see here. We can test primordial non-Gaussianity, and we could also test the neutrino mass with the SK low observations, for example. So people have written papers all about this, and there's also a lot about this in the red book if you'd like to see more details. Now, what I want to highlight is one much more sort of practical project we have done recently in the working group, which is we had a foreground removal challenge for SKA H1 intensity mapping specific. We did that within our working group because we are planning to use the SKA as a single dish. As I've just said, we want to just use a dish with a very poor resolution so we get to the really large scales. Now, we are pretty much, I think, the only working group who wants to use the SKA in that way. So we have to be pretty sure we know what we're doing in terms of data reduction and processing. So this was a point to start, obviously, because foreground removal is tricky. So we did the simulation of a sky patch. You can see here we obviously went away from the galactic plane, And we did that for the SKA as well as MeerKAT. So that I haven't really mentioned MeerKAT much. I should have done that before. That is basically an already existing part of SKA Mid. So that's 64 dishes in South Africa that are already producing loads of amazing science. And you probably have seen loads of it before already. And I'm going to show you a lot of data from MeerKAT as well during this talk. But this is for simulations. So basically, we produce these simulations for the different instrument, for different beam models as well. And we also tested different foreground models because we don't want to just have a foreground removal method that works really well with my foreground model, even though it might not actually be that much the foreground that we have in the sky. And then we gave that to people, and they didn't know what exactly went in, and they removed the foreground. And then they submitted it back, and we didn't even know which of the method was used for the foreground removal. So it was pretty much like a double blind practice. And all of these people down here in the bottom, you can see it's very much a proper group effort. Everyone contributed so much to this project. So you can see here maps of how it looked like when you have the different foregrounds and then noise and also H1 in it. And then this is just a comparison we did. For example, one thing, when you remove foregrounds, we use methods like PCA, principal component analysis. That's the sort of standard we use, but then there's also ICA or GMCA. Again, I don't want to go into too many details here. But one thing we always don't know is like how many modes do we remove? Like when we do a PCA, how many eigenmodes are actually the foregrounds, and when do we start to remove the signal? And so this was just a comparison of the choices people made, because it's usually a choice of the person analyzing the data. And you can see here we had loads of different data products, different beams. So it was very, very interesting, and it's all been published already in this paper. If you are more interested in that. And one thing that we basically, I just want to highlight, is we found basically a beam is a problem. If you have a beam which is not just Gaussian, but it has side lobes in it, particularly if you don't know the exact beam model, so you can deal with it in your foreground removal, that can be a big problem, and it can like create some sort of spike in your power spectrum when you remove the foregrounds, because it somehow interacts then with the foregrounds. It's very interesting, and so there's loads more work that kind of needs to go into that. We use the beam models correctly also during our foreground removal, because that interaction can cause problems, and we need to know more about that. So there's lots of follow-up projects now going on in the working group, which are open for people to join if anyone would be interested. Okay, so that was a bit about what's going on in the SKA currently, and now I want to talk a bit more about what we've actually done so far, show you results from the data. And I'll start with single dish intensity mapping. So we're talking poor spatial resolution. And this is the Green Bank telescope data, which was really the first to do this method. And that was very much published by Kiyo Masui and Eric Switzer in 2013. And they were the first to detect a power spectrum in correlation with galaxies, because the data is just not quite good enough yet. So we can measure just the H1 power spectrum. So we usually need a galaxy server of the same area and cross-correlate in order to detect the signal. And that's what I'm going to show you also now. So you can see here on the left, the H1 data. So if you look at that point source, that tells you also how big the beam is. For this data, the full width of maximum is about 1/3 of a degree. I apologize, I don't really have very good access on this particular plot. But this is what the data looks like. These are your foreground with all the foreground in. These are what the maps look like. This is your inverse noise, which again shows you a bit the scanning strategy. That can also be a problem. It's very anisotropic, the way you kind of scan the skies in the maps, which leads to that usually the edges can be very high noise. and then when we clean, leads to it being very dominant in here. So this is just an example of when we cleaned the data that you have still very anisotropic noise, sort of you can see too much structure in there. So we usually cut out edges and then we can improve it. So you can see that in a clean map here. This is 100 square degrees, and this is for redshift 0.6 to 1. And this was 100 hours observation, which could be interesting for later comparison. So what we then recently done is we took the initial data was somewhat less observation time, and it was also divided up in 2 areas. So they've added on more observation time to just one field. So it got deeper. And so we reanalyzed the data very recently in order to cross-correlate it with the EBOS galaxy surveys, which also had come out quite recently, in addition to the Wiggle survey, which was the initial detection in 2013. So now this is then the H1 intensity power spectrum that we got. So this is not a detection, this is an upper limit. And you can see here, it's getting now slightly a bit more technical. For the different colors are different choices of foreground removal. So how many modes you remove, where you would be very conservative in the dark blue and quite aggressive cleaning in the green. And then now the different shapes and symbols are, because we actually divided up all the data in 4 independent time blocks. So you have 4 times the data set so that the noise is independent in them. And so we actually look at then the cross correlation between these data sets rather than the autocorrelation of one when we measure the power spectrum. And you can see basically when we look at the auto, you basically measure the noise power spectrum. So this is the noise here, the noise level. And then when you do the cross between the data sets, we can push it further down. However, it is still systematics dominated, which are just present in all the data sets and correlate. But you can see that for sort of the modes removed, we start to converge to sort of one level, which makes you a bit more confident about your foreground removal doing the right thing. What we then do is we cross-correlate these H1 intensity map with the galaxies. So now one reason is that we need to do it in order to detect the signal. But the reason we are doing 3 different kinds of galaxies is that the correlation also depends about how much H1 is present in the galaxies that we're looking at, the optical ones. Because that is also something that correlates on top of the sort of cosmology large scale structure. We also have like an amplitude of an H1 mass that goes into the H1 intensity map. And now when we look at these galaxy samples, we have the emission line galaxies of the EBOS survey and the large luminous galaxies. We expect them to be relatively different. One is very H1 rich, the blue galaxies, the same as the Wiggles galaxies. They're quite H1 rich and they're quite star forming, whereas red galaxies we expect to be very depleted of H1, so they shouldn't as strongly correlate. So this is also one reason we use these 3 galaxy samples to check for that correlation. And now this is the H1 galaxy power spectrum. There's loads more plots and different ways, visualizations in this paper. I also said that Akisis Potsadu massively contributed, like we co-let the paper. But this is just one example of how they look like in comparison. This is for a quite aggressive foreground cleaning for the different samples. Now this going to 0 is very much expected. That's the beam. This was just washing out the signal. So that is all well understood and modeled. And we can then analyze the amplitude of this, of this cross power spectrum. We can't do any constraints using the shape because it's just way too noisy. But we can do the overall amplitude, and as I said, that is sensitive to omega H1 as well as the H1 bias, as well as this cross correlation coefficient, which comes from the correlation with the H1 and the galaxies. So here is now a table where we've done all the cases. So we've got different cases of foreground removal, but we can also do different cases of the scales we're using, because some scales are more dominated by systematics than others. And so if you look at the whole scale range, you get a slightly different answer for the constraint. You can see here, it's sort of going up here with the smaller range you're using, and that is an indication that this is not a constant factor, but that the H1 bias is indeed scale dependent. So you can see that tendency of the scale dependence when you do these fit on different ranges as well. And we can also see that we get different answers for the different galaxy samples, which is because R is different for the different galaxy types. And now this is just a very much simpler version of the outcome of our analysis, is that when we make some additional assumption about the H1 bias as well as the cross-correlation factor, we can then just do a constraint on omega H1, which you can see here in the black line, and in addition to constraints from other experiments as well. Okay, now I want to talk about very latest results. They have been, it's not quite accepted yet. It's a analysis led by Steve Cunnington and UKRI, with the PI Mario Santos, who has worked very, very hard to make this sort of single dish mode on MeerKAT together with the SKAO workable. These maps that I'm showing here from the MeerKAT data are 200 square degrees for a relatively small redshift chunk, which is, again, because of RFI, we had to get rid of quite a lot of the data, and it's only from 10.5 hours of observations, which is just fantastic. And these maps are based on the calibration pipeline and map-making pipeline from Jingying Wang, which has been published a couple of years ago. So you can see again, we have this, obviously the structure because of the scanning that we do. And then this is a cleaned version, which again, we can remove different numbers of independent components. And these maps are basically added together from 64 dishes. Not all of them worked at all times. So obviously there's some different depth in there, but this is a combined map from all of them. And then we cross-correlated these maps again with the Wiggles galaxies. So that's the same survey that we used for the GBT maps, but we're obviously in a different redshift range now. And you can see again, we have this detection up here in the power spectrum, as well as the fit you can see in here as well. Where again, the overall amplitude we fitted, which is sensitive to omega H1 B H1R. And you can also see here the detection significance in the second panel, and also the comparison to a null test where we just shuffled one of the data sets in redshift to see that we actually measuring a cosmological correlation. And it's not just some systematics. So you can see that going to null in the red one. So then this is a sort of visual representation of that table I've shown you before for our GBT analysis, where again, there were these different, you can see here we are firstly on much larger scales because the beam of MeerKAT is much bigger because the dishes are much smaller. And we're obviously also at a different redshift, 0.3. So you can see these at the red stars. And again, for different scales were used for the constraints, you can see again here the scale dependence. And then this is as a comparison actually from the data that I've just shown here in blue, what we found with the GBT data. You also, a very nice addition is here. You can see there is also a dependence of the number of the number of components you remove. So there's a lot of sort of choices which are not quite clear, and we just at this point where we don't have the deepest understanding yet what's happening and what's the right thing to do. That's just what we have to accept. But we firstly have much more data now coming in, and also much more work is going into identifying what's going on both with the RFI as well as with the beam as well as with the foregrounds. So there will be loads more work coming within the next couple of years from this. Okay, so now the sort of last 10 minutes, I would like to talk about interferometric intensity mapping, which I find very exciting. For the reasons that you can use the smaller scales for much more H1 astrophysics, and there's much more H1 astrophysics that goes into the smaller scales, so you can learn much more. So here I'm showing you again an H1 power spectrum. You've seen loads of them now. So this is now a forecast we did, just to give you an idea of sort of the surveys that are going on or will be going on. So we've got here the MIGHTY survey in yellow, which is a deep continuum and H1 survey at MeerKAT again. And then there's also DINGO, which is the ASCAP survey, equivalent deep H1 stacking experiment. Stacking is the main science goal. And then also as a comparison, how the SKA mid-band 2 survey would be. And so these are the noise predictions for them. So the shape depends now on how your dishes are distributed. So on your baseline distribution, that's what the shape is giving you. And then obviously the amplitude, there's loads of different factors that go in. And I've given, for some people who are very familiar looking at these surveys, I've given you here the numbers of obviously your dish, number of dishes, number of beam, the instrument temperature, your dish size, and then obviously also your survey area and how much observation time you have. So these are the assumptions we made, and some forecasts of how we can detect the H1 power spectrum. And you can see now on these small scales, we go into basically a shot noise regime very strongly, which is great because a shot noise, it can actually, as I said, the H1 shot noise has a lot of information. You can infer a lot of H1 from it. And it's actually just sort of an amplitude to measure, which is easier than a shape. So in order to infer H1 astrophysics from this power spectrum, and we developed this H1 halo model together with collaborators, obviously. And the main ingredients to go in here is a H1 to halo mass relation on the left, as well as an H1 density profile, so how the H1 density behaves within the halo as a function of radius. And it's a very fast tool, which means it's very good to also do analysis of data and fit H1 parameters to it. So the H1 parameters in this case would be the parameters that go into this H1 to halo mass relation, as well as the parameters for the H1 density profile. But we can then also, when we do these fits, and this is just a forecast, this is not a data fit, this is just a forecast we did for these 3 experiments, you can then translate these parameters in something a bit more that we can grasp easier, which is, for example, the H1 bias on scales. So you measure again the scale dependence of the H1 bias, or the H1 mass at certain of the halo mass relation, as well as again the shot noise amplitude. So you can see here sort of that we predict to measure these parameters quite well with these experiments if we were to have the full data. And then again, a slightly simpler version of just how we could measure omega H1 in comparison to existing data constraints, as well as sort of forecasts we have made. So here would be the two forecasts, and this is in comparison to data for a very low redshift. And here's for the higher redshift in the upper panel. These would be the forecast versus there's very, very little sort of data constraints yet there. But we can't, it's not only about omega H1. When you do these experiments, you can really measure scale dependence of an H1 bias and the shot noise amplitude, and the shot noise amplitude in turn can actually also measure you the H1 mass function. So you know how H1 is distributed, and that's something obviously very interesting, which tells you a lot about galaxy evolution. Another thing, which I'm not even going to mention much in this talk, is but you can also, if you combine these observations with galaxy surveys again, you can actually start testing the H1 content of the galaxies you're cross-correlating with, which is again in this magical cross-correlation shot noise. So it's a very interesting thing to do if you want to learn more about, you know, H1 gas and how it behaves with different properties. We've also worked on doing some more detailed data simulations, because obviously it's, again, we have the same challenges with mainly foregrounds and RFI. So again, we need to know how we deal with our data and what methods we use. So this is in recently submitted work led by Zhaoting Chen. He's created this visibility simulation with Oscar and foregrounds to put in. So you can see here the baseline distribution of this would be for a MIGHTY, so MeerKAT observation, one tracking. And these would be different foreground components like synchrotron 3.3 and point sources that go into these simulations. And then he's tested how well we can deal with the foregrounds and we can get the power spectrum back. And so now, because we're using an interferometric experiment, you actually measure your data in visibility space is nothing else than Fourier space, which is already what your power spectrum is. So you can also directly try to avoid your foregrounds in Fourier space and go directly to the power spectrum, or you can convert it into image space and remove your foregrounds there. So we've tested both of these methods, and on the left is an example how this is just the input point sources. This is just so you can see the point sources. They're made a bit bigger here, and then this is how it looks with foregrounds, and it's gone through our simulations. And then in the lower left panel, you can see how well we removed foregrounds when we used our method in visibility space, where we both removed some with PCA, as well as like a principal component analysis, as well as avoiding just simply some spaces of the foregrounds. And this is as in comparison how it would just look. Actually, it could be the other way around. I'm not entirely sure now, but that's a good thing. They look so similar. I'm actually not entirely sure which one is the foreground removed one and which one is the one where he actually only put H1 signal through the simulation. And here you can see a similar thing from in the power spectrum space, where we tested all of these different ways of either avoiding foregrounds by using just modes within a certain window, or applying a PCA in sort of different domains, either visibility or image space, which is important things to be confident of your results. And I'm going to end with showing you actually interferometric MeerKAT data for H1 intensity mapping, which is really, really exciting. So this is at 2 redshifts of 0.3 and 0.44 that we have some data observations which are clean enough from RFI. And this is it was a deep 2 observations, and this is then what if we were to convert our visibility data into an image. This is what it looks like. This is obviously mostly our radio sources in it. This is the foregrounds basically. So this work is in prep, so please don't share it yet. This is with 96 hours of observations, and some quite vigorous RFI flagging again had to go on in order to do that. And then we can actually go, I'm showing you here the 2D power spectrum. So this is again a power spectrum like I've shown you before. You can see here in the sort of units, Kelvin squared, megaparsec cubed. But we've got it now in the K modes. So one is transfers, which is this one. There's the parallel ones, which are coming from the frequency channels. So this is from the frequency channels, the information, whereas this is from the sort of image space, if you want. And in the left is the data, and on the right is our simulation. This is not a simulation I've just shown you. This is a slightly different simulation based on a slightly different pipeline, but we're also now testing our pipeline on the same data as well. And so what you can see in here is that point sources are located down here in red. And there's a lot of noise going on the smaller scale, so you want to avoid all of that. So basically what you use for analysis is all data within this sort of black dashed line, and this is how we avoid the foregrounds. And then now I'm going to leave you with that as a very, very big cliffhanger and say stay tuned for more of that data, as we are not entirely ready to share the outcome yet, but it's a very exciting space to be working in at the moment. So I'm going to leave you with my summary. I hope I've convinced you that H1 intensity mapping can be a really useful probe, not only for cosmology, but also to constrain H1 properties in actually multiple different ways. We have first MeerKAT observations, and we keep getting more and more data in for both single dish as well as interferometric mode, and they can test then the whole range of scales. In both scales and in both modes, we have the biggest challenge by RFI and foreground, so we have to put all our efforts now in to understand that. And then hopefully there will be more exciting data and results coming soon.
Thank you very much, Laura, for this wonderful talk. Now the talk is open for questions. And for doing that, please raise your hand, and I will ask Teresa to manage all this section. Please, Teresa.
Hi, thank you so much, Laura. This was a great talk, and I think cosmology SKA usage is something I'm the least aware of, so I'll be looking forward to it, and it was great to get a kind of a view into this area. Are there any questions? I'm going to see, could you possibly close the screen, because then I can see if people are raising their hands. Perfect. And if there are no immediate ones, I have a crap load. I'll do the rest of your chats first then. Okay, so one of my first question is, I'm very intrigued about this prospect of using an interferometer array as a single dish telescope, and I just wanted to make sure I got this correctly. You're talking about using the entire array as a single dish, or just the separate antennas?
Yes, so you use every antenna as your single dish, and then you combine all the data later.
Okay.
So you obviously, the big challenge there is the sort of calibration, to get the calibration, because that's not the standard mode, and so that's what a lot of, I mean, not me, I don't, but a lot of people work really hard in South Africa to make this happen. Because only if we manage to do that with MeerKAT, we can, because loads of cosmology on H1 intensity map with SKA is based on using the SKA in single dish mode. So if we can't make it happen with MeerKAT, so it was great to see now these results, that we can actually use the data.
Mm-hmm. Okay, so that answers my second question about them not being large enough to be sensitive enough. And okay, this is really cool. Very useful. I've never heard of this before, actually. So, and it brings me to another question. What kind of sensitivities are we talking about for these measurements in say microgenesis? What kind of RMS noise do you need to reach?
Oh God, yeah. Now you've reached me, because I am a cosmologist and not a radio astronomer. I cannot tell you.
That's okay.
I am so sorry. Yeah, because I never sort of deal much in Danskis, and I need to get much more in it. The more we deal with the data, and the more you become a data analyst versus someone working on methods towards. I'm so sorry.
No, that's okay. Do we have any other questions before I go into my pile? I don't want to hog the conversation here, so speak up. I saw a message in the chat. Okay, let's do this. Some of my questions are quite instrument specific, so maybe I shouldn't go too much into details there. But one thing I was wondering about is, apart from, you're the only group that would be doing this using the array as a single dish, but is there any ability to use other data from other projects, other working groups as well in the interest of commensality for these projects?
Yeah, that's a really tricky question. There is at the moment we need to start investigating that, basically, because in order to have the stability for the calibration we need, and again, I'm not the expert, Mario Santos is working really hard on that, and Keith Grange, for example. In order to do our scanning speed for the calibration stability for the single dish, that still is commensal with the visibilities you're getting out. Because you might have seen in our SKA Cosmology surveys that we are planning to do at commensal this 20,000 wide with the continuum radio, which means that they want to do, they use not the single dish data, but the visibilities. So at the moment we are starting now again with the MeerKAT data to look into that. And very recently, like, how can you use the visibilities from our single dish scanning? And very recently, I think in the last sort of month or so, Christoph, I forgot his last name, managed to actually get an image out of the visibilities for the first time. It was a quite complicated thing because of something with the face center and things like that. So yes, if we manage to make that work, yes, then that opens a lot of doors, because we obviously need a lot of time. But it's the answer. We're investigating now with MeerKAT.
Okay, excellent. Thank you. That is indeed very exciting. Okay, any other questions? Otherwise, I think we'll thank you again very much for taking your time to give us this talk. And René, over to you.
Yeah, thank you again, Laura, for this nice talk. And thank you, Teresa, for managing all this section. And see you in the next talk in September.
Thanks so much for having me. It was really nice. Thanks.
So I stop recording now.